All right, hi everybody. So here is the video for absent students on activation energy and energy transfer. So the first thing you want to do before anything else is read through pages 1 to 2 right there up until the data analysis. And you're going to highlight or underline any main ideas, vocabulary, and concepts. Okay, so go ahead and pause the video and go ahead and do that. After reading through, and this is kind of a review of our notes from Friday, activation energy is our energy that's required to start a reaction. We have endothermic and exothermic reactions and their potential energy diagrams. And what the data analysis has you do is practice graphing this, okay? So in Teams, there should be a link to the data sets. There is a data set for A2 plus B2 goes to 2AB. And then a data set for C2 plus D2 goes to 2CD. So you're gonna graph two separate graphs. And when you guys make your graphs, essentially the thing that I see students struggle with the most is making the intervals. So your x-axis should be your time. Again, we wanna always include the unit because time we can measure in minutes, hours, seconds, lots of different things. So time in seconds. And then on this one, we have energy in kilojoules. Okay. Now, if we look at our data, the highest number it goes up to is 15. But if I count over, I only have 9 grids. So I can't go by ones or else 9 would be here and I still need 15 left. So what I would do is I would go by 2s. So before you start graphing your data, you need to make sure, right, that you have all your intervals listed. 12, 14, 16, right? We don't even need to put 18 because our data only goes up to 15. And then for kilojoules, our highest number is 100. And we have 10 grids, so that makes it easy to go by 10s. So I'm gonna go ahead and go 10, 20, 30, 40, all the way up to 100. Ignore that tick mark, that was off. Okay, and then you're gonna go ahead and graph your data. So you should graph your points. For this one, you're gonna connect the dots, all right? On your data set, so you'll graph this way and you're gonna do the same exact intervals for your CD graph as well. On your graph, you're going to label the reactants, the products, the activation energy, and whether it's endothermic or exothermic. And to kind of reference how you do that, look back at the examples on the first page, right? And use those to guide you labeling your graphs. So that's kind of like our prerequisite conceptual knowledge before doing the lab. When we get to our lab portion, this is our lab. We did it a little bit differently in class. So what we used is we used a soda can calorimeter. And we put it up on the ring stand, so kind of like this. Like this. We got 25 milliliters of water and we poured it into our soda can calorimeter. And then we used the paper clip as a stand to burn our food item. So we kind of just set it up just like this. If you could see. And then what we did was we took an initial mass of our Cheeto before and an initial temperature of our water before, because what we want to see is how much mass we lose of the Cheeto and how that mass is going to correspond to how much energy is transferred to the water, right? And then we're going to find a temperature change so that we can use our Q equals MCAT formula to do our mass of our water times specific heat of our water times our temperature change of our water. So we just lit our food item, right? Let it light. It heated up the soda can, right? The flame. We tried to adjust it as best as we could to keep that heat source as close to the calorimeter as possible. And then we allowed it to burn for approximately a minute, blew it out, took the final temperature, took the mass of the Cheeto after, and that was pretty much our lab. So what I want you guys to do is to go through using this data, pretending that you did the lab with this data, okay? So we have our mass before and after, and our temperature before and after. So with the analysis questions, based on the data collected, how did the mass change? Well, we can see that there's a decrease, right, in our mass. Does this investigation follow the law of conservation of mass? Your answer should always be yes, but why? So essentially, when you burn a food item, I guess I could do it really quick, just for example. Okay, so that's kind of going. We're gonna see that we lose our mass of our Cheeto, but I don't know if you can really tell in the video. Let's blow it out. See all the smoke that comes off, right? So when we burn something, we know that smoke is produced, we know other things are produced. So even though you might have lost mass, where do you think the mass goes? That's your answer to number 2. Number 3, based on the law of conservation of energy, describe the energy of the system at the beginning of the reaction and at the end of the reaction. Okay, so we know that the energy starting in the Cheeto, right, specifically as potential energy in the bonds, and then how is that energy transferred? Where does it go? What does it heat up? So on and so forth. Number 4, cross out number 4. We didn't do number 4. And number 5, so we did 2 different food items in class. We did a Cheeto and a Cheerio. The Cheerio is a little bit easier to light than the Cheeto. So we would say that the activation of the Cheerio is less than the activation of the Cheeto, just because it was easier to light. So it took less energy to get the reaction going. Remember, activation energy is the energy needed to start the reaction. So if a reaction happens very quick, right, that's a low activation energy. If the reaction doesn't happen as quickly, that's a higher activation energy. Now, on the back of your paper is blank. Right, but this is where we ended up doing some extra math, okay? And I have these questions linked in Teams, the food calorimetry math. So you want to just put your answers to these on the back of your paper, okay? So I'll just put it on this paper just for ease. So using your data, calculate how much energy your water gained. We want our number in calories, so use 1 calorie per gram Celsius on your specific heat. So a couple things. We know we're going to use the Q equals MC delta T equation, okay? Remember that the mass of the water, well, if you look back at our procedure, I said that we added 25 milliliters of water. Okay, so we added 25 milliliters of water. So your mass isn't coming from your Cheeto, because remember, this is the energy that the water gained. Okay, so your mass, if we added 25 milliliters, remember 1 milliliter is equal to 1 gram. So we should have 25 grams times our specific heat. Now I told you in this case, since we're going to calculate calories, we're going to use this number as our specific heat. And then our change in temperature, remember, is our TF minus our TI, using the data that I gave you on the previous page. Right, so if you need to, let's go ahead and let me put that over. This is your absent data. So go ahead and pause the video and write in your absent data. All right, so again, for your absent data, you're using your final and your initial temperature. You're gonna plug in your numbers, and you should get your answer in calories, right? So whatever you get in calories, okay? How much energy did your Cheeto lose? How do you know this? Well, what heated up the water, right? So if we know that the water gained you know, let's just say it was let's say it was like 600 calories. The water gained 600 calories. How much can we assume that the Cheeto lost? Okay, so number 2, you want to answer that. Number 3, convert Cheeto calories to kilocalories. So the number that you get for your Cheeto calories, again, you don't need to do math here. It's just a conceptual thing. Think about how when we did the Q of the water equals the Q of the metal, right? But now we're talking about Cheetos. Okay, so whatever you say your calories is for your Cheeto, you're going to convert that to kilocalories. If a kilocalorie is 1,000 calories, well, then that means I need to divide that number by 1,000 calories to get my answer to number 3 in kilocalories. Okay, so that's how you're going to do. You're going to take your number that you say for your Cheeto, divided by 1,000, and that is your number of kilocalories. For number 4, calculate how many kilocalories per gram your food item contains by dividing your kilocalories by the mass lost by the food item. So you're going to take your answer to number 3 in kilocalories, and you're going to divide it by the number of grams that you got from your data table. So you're going to look at how many grams was lost, right? How many grams actually burned, right? So you might have to do mass by difference. You're going to take that number, plug it in there, and that's going to be your answer to number 4. Your unit is going to be kilocalories per gram. All right? Now, number 5, find your percent error. Our percent error is equal to our accepted minus our measured divided by our accepted times 100. So in this case, this number is our accepted. Okay, so you're going to put in your equation percent error equals our accepted. Well, that's 8.7 minus whatever your number is to number 4 divided by our accepted again, which is 8.7 times 100. That is our percent error. All right, so you're going to get some percent. I'm going to tell you, it is a high number, very high. Okay, so in number 6, where does all the energy go? Why is there such a large percent error? I want you to think about the design of your lab, why a lot of your energy might have not heated up the can. Okay, where else could your energy go? And then number 7, you're going to suggest 2 improvements to the lab design or procedure in order to decrease our percent error. Okay, so thinking about, you know, how could we improve this lab to make it where we're not going to lose as much energy, because we have a very high percent error, which means that we were off. Okay, and that's essentially how you will make up the activation energy and energy transfer lab. All right, thanks for watching.